5. Let omega contained in Rn be an open set. Let u belong to Lp of omega 1 less than p less than or equal to infinity. Assume that there exists a constant c which is greater than or equal to 0 such that for every phi in d omega and for every 1 less than or equal to I less than or equal to n, mod of integral on omega u d phi by dxi dx is less than c times mod phi 0 p dash omega, where p dash equals conjugate exponent. So, if p dash equal to infinity, then if p equals infinity implies p dash equal to 1. If 1 less than p less than infinity, then 1 by p plus 1 by p dash equal to 1. Okay. So, show that u belongs to W1p of omega. Solution. So, you have to show that the first distribution derivative is in Lp. Okay. So, now consider L of phi equals integral u d phi by dxi dx. Then mod L phi is less than or equal to c mod phi 0 p dash omega. So, phi going to L phi is a continuous linear functional on d omega with the norm mod 0 p dash omega, but p not equal to 1, therefore p dash is not equal to infinity. So, this implies that d omega is dense in Lp dash, implies L of phi extends uniquely to, so phi going to L of phi, a continuous linear functional on Lp dash omega. So, by Rees representation theorem, there exists Vi 1 less than or equal to I less than or equal to n. So, okay, so let us, I call this Li 1 less than or equal to I less than or equal to n. So, mod Li phi and then Li phi extends. Okay. So, there exists Vi in Lp of omega. This is the dual of Lp dash, because p dash is not equal to infinity, remember that. So, the dual of Lp is always Lp dash, Lp dash is Lp. Okay. So, only for L infinity you have a problem which we have avoided now. So, such that L of phi equals integral Vi phi omega dx for every phi in d omega. Okay. So, this implies that du by dxi equals minus Vi, which is in Lp of omega, and therefore this implies that u is in W1p. 6. Let omega contained in Rn be an open set. Let 1 less than or equal to p less than or equal to infinity and u in LP of omega. Assume there exists a C1 greater than 0 such that for every omega prime relatively compact in omega and for every h in Rn such that mod h, that is its Euclidean norm, is less than the distance of omega dash from Rn minus omega. So, you have omega, this is omega dash, this is omega, this is relatively compact. So, the distance between Rn minus omega and omega dash, so this distance is d and mod h should be less than d. We have mod tau minus h u minus u 0 p omega dash is less than or equal to c mod h. Let me call this star. Then there exists c greater than 0 such that, okay, show that, such that for all 1 less than or equal to I less than or equal to n, for all phi in d omega, we have mod integral on omega u d phi by dxi dx is less than or equal to c times mod phi 0 p dash omega. So, this is the inequality we had in the previous exercise. So, in particular, by exercise, what's the number? We are 6 now. So, by exercise 5 above, if 1 less than p less than or equal to infinity, we have u is in W1p omega if star is true. So, this is a characterization. So, when you want to show the derivative, you want to show that this is something, the tau minus h is a translation. So, it's tau minus h u of x is u of x plus h. So, you are saying u of x plus h minus u of x in LP norm should be bounded by h. So, that means the derivative is controlled. Now, why do we take for relatively compact sets? Because you are taking u of x plus h. If you take the plus h, then you want it to stay still inside the domain of definition, and that is why you want to take a smaller set omega prime, and if you apply u of x plus h where h is less than the distance between the two sets, then it will still be in the big open set. Okay, so solution. Let u tilde be the extension of u by 0 outside omega. So, u tilde belongs to LP of Rn. Let phi belong to d omega and let omega dash relatively compact in omega such that support of phi is contained in omega dash. So, I equals 1 to n standard basis vectors of Rn. That means it has 1 in the ith coordinate, 0 in the other coordinates. And let h in R mod h less than distance of omega dash from Rn minus omega. So, now if you take integral on omega ux phi of x plus h ei minus phi of x divided by h dx. Okay. This is equal to integral on Rn u tilde of x phi of x plus hei minus phi of x by h. Now, because I am in Rn, I can now write this. This is equal to u tilde. If I make a change of variable for the first product alone, so that will give you u tilde minus y minus hei minus u tilde of y divided by h phi of y dy. But now I have brought everything into phi, and therefore this becomes just integral on omega dash, because phi outside omega dash everything is 0. So this becomes u tilde y minus hei minus u tilde y by h. So support of phi is in, that is why we have done it. Now mod h is less than d of omega dash Rn minus omega. So hei is a vector whose Euclidean norm is less than that. So if y belongs to omega dash, you have that y minus hei belongs to omega itself. So this implies that integral on omega ux phi of x plus hei minus phi of x by h dx equal to integral on omega prime u of y minus hei minus uy by h phi of y dy, which is nothing but integral on omega dash tau of hei u minus u acting on y phi of y dy, and that is less than equal to c times mod phi 0 p omega prime p dash by Helder. So 0 tau hei u minus u in LP, we are using star. So this is Helder and star. So you pass to the limit as h tends to 0, and dominated convergence theorem will tell you that integral on omega mod u d phi by dxi, because pointwise this converges to d phi by dxi, and it's all, this is bounded and this is u is in LP, so there's no problem. So you have that this is less than or equal to c mod phi 0 p dash omega dash, which is less than or equal to c mod phi 0 p dash omega, because omega dash is in and that is, this is exactly what we wanted to prove, and that completes this thing.